This is intended to be recording in progress. This is intended to be interactive here, and this is the second of this kind of presentation we've done. So just by way of quick history here, we've been doing regional seismic planning at least for since 1990. We did a regional seismic study with Cigna, the consultant, in 1990, did a lot of seismic upgrades as a result of that in the region. And then as we were starting to understand the effects of the Seattle Fault and the Cascadia subduction zone, we finished another study in 2018 for the same regional system, in which we found that the levels of shaking and ground displacement were much higher than anticipated in 1990. So in 2018, we released the study, and as part of the outreach, we did a presentation very similar to this, except it was in person, pre-pandemic, over on the east side, and I think about half of you I remember seeing there. And the intent is we want to make sure that as wholesale customers, you have buy-in and that you see what we're doing regionally, because you help pay for all of these capital and O&M type of improvements. So in terms of overall discussion here, you all probably know that we meet with Cascade on a quarterly basis to talk of topics of interest. We meet as needed on a daily basis if there are operational issues, and you should always feel free to call our control center if there's something going on. And when there's particular topics where you as Cascade members want to speak directly to Seattle Public Utilities, we're always there to facilitate that discussion. Seismic just happens to be the one topic that you've all asked for. But if you have other things you're interested in, we're happy to work through Cascade to talk to you about where the regional system gets its water from the Tolt and the Cedar to all of you. So that's just my preamble here. The first presentation we gave was focused on why did we do another seismic study? What did we find? Generally speaking, things that did okay in the 1990s level of shaking don't do as well in the 2018 level of shaking. No real surprise. The other thing is that there's a lot of capital improvements needed, and we can't afford to do all of them right away. So we went and prioritized them from most important, most critical, highest risk to least. And we came up with an approximate 50-year plan of seismic improvements, mostly focused on capital. So if you recall, that's what we told you about 4 years ago. Today is an update of that. So we've done another supplemental study focusing on some other portions of the transmission system, the piping. We know, for example, Bellevue has said, we'd love it if you could prioritize the Cedar Eastside supply line more than you originally did in the 50-year plan in 2018. And what you'll find is that with that supplemental study, that we're starting to learn more about some of the site-specific needs here, and that's caused us to adjust the 50-year plan somewhat. So there's some good news baked into there, and I don't want to steal Bill's thunder, but Bill, am I missing anything from kind of a 10,000-foot level for this group?
No, you're doing a good job. In fact, go ahead and steal my thunder. I'll just
yeah. Bill tells a good story, and I would just at this point suggest let's bring up the slides and have Bill tell you what we've learned since we talked to you 4 years ago.
Hopefully you can see my screen now.
Good to go.
Okay. This is not, just a second.
Bill, if you're speaking, we can't hear you.
Can you hear me now?
Yes.
Okay, I'm having trouble bringing slideshow up for some reason, and so I'm just going to do it in this mode. I don't know what's going on. It worked well 10 minutes ago, but not even working that way. Okay, so anyway, this is a presentation, a seismic program update on SPU's seismic program. I'm going to start out giving a summary, which Alex has already done a little bit of what we've done in the past and what our objectives are. I'll go over some specific project updates geared towards transmission systems. We essentially completed what we called our transmission pipeline study and are in the process of developing a plan. It's getting near to being a final draft. And then I will go over some updates on Eastside and Renton reservoir assessments. And then just a final slide is basically the 10-year plan for transmission pipelines or transmission system. And I think most of you have already seen the slide. It's from March and there's very little change since then. So essentially, as Alex mentioned, there's a rental study done back in 1990 by Signet Energy Services. And we updated that study in 2018 using the latest ground motions. And not surprisingly, there were some additional facilities identified in the 2018 study that weren't identified in the 1990 study just because the ground motions have increased. The biggest takeaway from the 2018 study is the vulnerability of our pipelines, and that's both the distribution pipelines and the transmission system pipelines. On the distribution side, we're looking at possibly 1,400 plus or minus distribution pipeline breaks after a Cascadia magnitude 9 earthquake, and maybe upwards of 2,000 distribution pipeline breaks from a magnitude 7 Seattle fault event that occurred within Seattle. On the transmission side, we looked at probably 70 to 80 sites overall and identified a number of vulnerable sites that had not been identified in the 1990 study, again, just because of the increased ground motions that we're getting from the Seattle fault zone and southward beyond the fault zone. To mitigate all this, we came up with a long-term plan. And by long-term, I'm talking about 75 to 100 years. That $800 million is not over 10 years, it's over 75 to 100 years, which is still a lot of money, but it makes it a little bit better. We came up kind of with an idea that we'd have a short-term and long-term approach. The short-term approach is essentially using emergency response planning, possibly isolation control, and some other measures to stop the bleeding if an event occurs before we can do substantial upgrades. The longer-term plan is to upgrade some of our most critical facilities, but also to use seismic design standards to make sure that what we build new when we place infrastructure, just through asset management purposes, whether it's condition related, operational related, or whatever, so that we get it built right, and so we don't have to come back and upgrade it later. As I mentioned, we recently completed the transmission pipeline study last year, and so I'll be going over some of those results in a little bit more detail. Again, it's a long-term plan. It's a long-term program. We're not going to be able to fix everything tomorrow or upgrade everything tomorrow. The purpose of these next two charts is basically not so much as to argue whether it should be 2 months or 6 weeks for 2045, but to show that things are generally going to get better, but that's going to take some time. And so these are the 2045 performance goals out almost 25 years. As you can see, there's still going to be, if there is a major earthquake, there is still going to be some significant damage and some significant recovery that's involved. Going out to 2075, more than 50 years from now, things get a little better. If you're looking out maybe 100 years, that would be my vision for 100 years would be if we had a major earthquake such as a magnitude 7 or a magnitude 9 earthquake on the Cascadia conduction zone, it would look somewhat like it looked after the Nisqually earthquake. That is, it's still going to be a big deal, but it's not going to be a disaster where you have people without water for a month or two. And so to try to meet these goals, we came up with a long-term plan. This is out of the seismic study. And so far, well, it's only 4 years, so of course we're mostly on track. Where we're falling behind a little bit are on some of the projects that are more internal labor intensive. For example, the seismic isolation valve, we haven't really gotten very far in that. And we've been running into manpower as far as getting emergency repair materials so that we'd have those in stock if there was a major earthquake before we could upgrade things and we had to make emergency repairs. And so those are proceeding, they're just proceeding a little bit behind schedule just due to staffing issues. As far as some of the CIP projects where we're hiring consultants, those are pretty much on track. So shifting into some of the projects that have recently been completed. Late last year, we got the final report for the transmission pipeline study. There are actually 3 studies within a study. The first was what we call the 50 site study. And that was looking at approximately 50 sites that we didn't have the resources to get to during the original seismic study. And so we hired Infraterra as a consultant, and they went out to all these sites. Actually, there were 53 or 54 sites, and looked at available soil borings and made some assessments as to the vulnerability of these different transmission pipeline sites. We also did preliminary engineering for the Cedar River pipeline and Renton site. Cedar River pipelines 1, 2, and 3, they go through a liquefiable area. It's a low area. And we identified this as original seismic study as being vulnerable. And so, like I said, Infraterra did some preliminary engineering and came up with some recommendations. And then finally, the third study within the study was looking at what would happen to transmission pipelines if there was fault rupture, and making some estimates. Okay, well, what type of pipe would be needed if we wanted to resist potential fault rupture? So shifting back to the 50 site study, this is an example site form that was done for over 50 sites. It basically describes a pipeline. If you look down here, it shows potential settlements and lateral spreading for 4 different scenarios. This happens to be the Eastside supply line, Coal Creek crossing. As you can see, what's driving it down here is the Seattle fault and the 2475 ground motions. And so the 2475 ground motions are going to be higher than any of these 3 scenarios, since the 2475 ground motions take into account all scenarios. But what you get from the site is where you can have some significant settlement or lateral spreading from a Seattle fault event. And so this was site was rated as potentially needing upgrade. Showing another example, this is just a little bit further south on the Eastside supply line. This is the May Creek ravine crossing. With May Creek, it's not lateral spreading or settlement, it's more slope stability. But again, there's just some potential vulnerability in there. Finally, using a third site example, this is out on Toll 1, also a concrete cylinder pipe. What's a little bit different from the Eastside supply line sites, what driving this site is the South Woodley Island fault, this purple line. It's not the Seattle fault. And so what that basically means is the same event that causes you problems on the Eastside supply line will not cause you problems on the Toll 1 pipeline, at least out here near the treatment plant, or somewhat close to the treatment plant. And so that's important to note. And
Hey,
so,
Bill,
yes.
there's a question in the chat here. Josh from Kirkland just was asking about the previous slide with the % of meters on the service level recovery. Is that referencing the number of wholesale meters we aspire to have active?
Oh, so we're going up here. This slide, I think, is what he's talking about.
Performance goals.
Yes.
Water supply at performance at wholesale meters.
Correct. That's a % of wholesale meters.
Okay, thanks.
Thank you.
Carry on.
Okay.
I'll monitor the chat.
Okay. Yeah, I can't see the chat since I'm doing it in this mode. If you want to wait 15 minutes, I could try to troubleshoot it, but we'll move on. So this is basically a compilation of all the sites that are vulnerable. That would be moderate to high or high vulnerability if they were exposed to the 2% and 50-year ground motions. That's a 2475 year event. And so what's important to note is that event, those ground motions, those probabilistic ground motions are not going to occur at all sites simultaneously. And so this looks bad, but it would not be this bad for a single event. And as an example, moving down, this shows for the magnitude 7 Seattle fault event we looked at. And so you can see there's still a significant number of breaks that affect just about all the transmission pipelines, but it's not quite as bad as if the 2475 motions were to occur simultaneously. What's kind of interesting and why I use the May Creek and Coal Creek slides is if you look up here, Coal Creek is still being shown as vulnerable during the Seattle fault event, but May Creek is not. And so what that's really saying is that for May Creek to have problems, the event would have to probably occur closer to May Creek than the event we assumed during our analysis. And so that's important to point out, is that there are a multitude of different scenarios here. And so we looked at 3 or 4 discrete scenarios, but there are a multitude. And so there is some uncertainty in all this. Going down, this shows the vulnerabilities for magnitude 9 Cascadia subduction event. As you switch back and forth between the slides, you can see that there are some commonalities, but some that are not common, as I just pointed out. So this final slide here, or on the 50 site study, or at least picture on the 50 site study, I wanted to point out the concrete cylinder pipe where we have that, and the turquoise lines are the lines where there's only a concrete cylinder pipe and there's nothing else. If you go up here, you have TOLT 1 and TOLT 2. TOLT 1 is concrete cylinder, but you have TOLT 2, which is steel, so that didn't get highlighted. And what I'm trying to point out from this is concrete cylinder pipe typically will last 60 to 125 years. Our concrete cylinder pipe, a lot of it, or most of it, was installed in about 1960. So over the next 50 to 60 years, most likely scenarios, we're going to have to either replace or rehabilitate this pipe anyway. And so as we were putting together a plan for upgrading transmission pipelines, it's kind of like, well, if we're going to have to replace it so soon anyway, does it really make sense to go ahead and upgrade it just for what could be, as short as 20 to 30 years when you're going to replace it anyway? And so we're kind of thinking along the lines that instead of going and trying to proactively upgrade these concrete cylinder pipelines, we'll just wait till they need to be replaced. And then when they do get replaced, make sure they're seismic resistant. And that kind of feeds into the next slide, which is a philosophy. We're only looking at vulnerabilities to liquefaction, landslide, or ground shaking. We're not looking at upgrading lines just because there's fault rupture. And I'll talk a little bit about that in a second here. Again, as I mentioned, we're only going to be looking at upgrading lines where we have a significant amount of useful life left. If we have a steel pipeline where we think we have 100, 152 years or 200 years left, that would be a candidate for upgrade. If we think the pipeline is probably going to need replacement for some other reason in the next 30, 40 years, then we'll just wait till then. When we do our upgrades and design for replacement, we're only going to look at liquefaction, landslide, and ground shaking hazards. We do not plan, at least at this time, at looking at fault rupture hazards. This is really open to debate. Down in California, what I will tell you is when they have a fault crossing, even if it's 2 miles long or plus, similar in length to some of our fault zone crossings, they will use pipe that can resist the fault ruptures. It's a little bit different story up here in that in California, the return intervals for these fault ruptures are shorter than what they are for the Seattle fault zone and the Southwood of the Island fault zone. So it muddles things up a little bit. Muddling it up a little bit more is, I'll show a slide later when we do look at the fault zone pipe that shows that if you do use earthquake resistant pipe for the fault zones, you get really a lot better performance. But right now our planning is not to design for fault zone ruptures. As far as geographically where we're going first, we're going to prioritize the Cedar River transmission system. The reasons for that are, number one, you can supply the most customers out of that system. Number two, it's primarily steel pipe that has significant remaining useful life. And so we'll be looking at going basically up from Lake Youngs up through Seattle and up to Lake Forest Park. Our next priority will be going northward on the east side supply line. Again, from the Cedar River crossing up, actually really up to the toll junction. And then the last priority would be going westward from the toll treatment plant, the toll pipelines. Again, a lot of these pipelines are concrete cylinder pipe, which are going to be replaced in the not too distant future, relatively speaking, anyway. Does anybody, I'll stop here because before I go into the Cedar River assessment, if anybody has any questions or comments or.
Feel free to mute and ask questions or post to the chat, either way.
You can wait till the end of the presentation. I just thought in case anybody, before I switch subjects here a little bit.
As a quick reminder of how the system works here, generally speaking, the Cedar system serves about the lower 2/3 of the regional system, toll the upper third, but it varies considerably from day to day, week to week, depending on the water supply balance and operational needs. In a pinch, we can serve Cedar water all the way up to the toll treatment plant, all the way up north and east. We can serve Cedar water pretty far down south, not all the way down to southwest Seattle. And one of the reasons we have the wells by the airport is so that we can supplement some of that, that supply needs down there in an emergency. So for those of you worried about the east side supply lines, absolutely a critical point. Another way to get water to you would be from toll going south versus Cedar going north. So there's a lot of flexibility in the system we're working with here.
Okay, I will proceed.
Linda DeBalt had a question in the chat.
Oh yeah, Linda's question is, in the next priorities category, what would be the approximate timeline for these upgrades?
I'm going to guess for the east side supply line, it's going to be around 30 years, 30, 40 years. And at that point, I'm guessing that they'll be talking about replacing those pipelines anyway. One thing I'm going to mention about concrete cylinder pipe is it's fairly brittle. And although we identified some point locations where we know we had some, unstable ground, it's really anywhere along those alignments you could have issues if there's any sort of ground movement. And so, for like the Cecil, we, identified May Creek and Coal Creek, but anywhere along here where there, some sort of unanticipated ground movement, just because the pipe is so brittle, there could be issues. And so for me anyway, to feel entirely confident about the Cecil, you'd have to have steel pipe through all of here. Okay, I will move on to the Cedar River and Renton alignment. This was an area that was identified during the 2018 study. So as part of the transmission pipeline study, we began the preliminary engineering on this site right here. And I think most people are familiar, the Cedar River pipelines drop down through utilidors under I-405 and traverse through Renton, and they cross the old Black River Trent Channel before heading back up the hill into Seattle. The news was kind of good for this part of the study, and that we thought, when we did the high level study, we were looking at settlements and displacements that would be greater than a foot or so. And when we started looking at some of the borings, and that's what these dots here are, these are actual soil borings that we had available during the study. We had a couple places where the displacements are in the order of 5 to 10 inches, but certainly not on the order of a foot or so that we were suspecting that we'd have during the original seismic study. This is showing the lateral spread, that is, the soil liquefy and would move laterally, most likely towards the Cedar River right here. Going to the next slide, where you have the settlement estimate. This is just pure settlement. Again, you have some areas or through here that are 5 to 10 inches, but they're certainly not the 12 to 18, 24 inches that we thought that we might have during the original seismic study. So that was kind of good news. Where we did find some problems were at the utilidor interfaces. And so what happens is the pipelines come down through these utilidors under I-405. They're kind of free to travel through this external wall here, but this first internal wall is fixed. And right here, there's a flexible coupling. And so the concern is that the soil liquefies here, the pipe wants to move longitudinally, it can move longitudinally, and when it hits this flexible coupling, the flexible coupling would simply just pull off and break the pipe. So that was the first area of concern we identified during the Circle and Renton study. The next area is the Black River Channel. And so circles 1 and 3 are supported on these pillars here. And the pillars actually stand below the liquefiable soils in the good soil. Circle 2 is direct buried. And in the Black River Channel itself, it's direct buried in good soil. However, it comes down the slope of the old channel in poor soils. And so there's concern about potential differential displacement with Cedar River Pipeline number 2. And this is just showing some diagrams of the saddles that support 1 and 3, and then obviously an elevation view crossing. The purpose of this slide here right now is just to show that Renton is a low spot, which I'm sure everybody here is aware of. What it means as far as pipeline assessment or vulnerability / consequences is, first of all, the pressure is 200, the static pressure is 200, 205 PSI. So there's a lot of pressure down there. The second thing is it is a low spot. So if the pipe breaks, there's an area that's going to, or a significant area that's going to be flooded. This is some of what you're thinking about or struggling with. These are the worst case or the finite element results showing the strains, both the tensile strains and the compressive strains in all 3 pipelines. The reason these numbers are circled is the circle numbers are the best estimate of the permanent ground displacements and the best estimate of the soil stiffness. And so the criteria here for both compressive and tensile strains was 0.32%. And so if you look at all these circled numbers, all the circled numbers are below, mostly significantly below 0.32%. If you look at some of the worst cases where you assume the 84th percentile, the permanent ground displacements, or the upper bound on the stiffness, then you start getting some of these bolded numbers that exceed the 0.32%. And so if we look at the best estimate of a low probability event, we're getting strains that are probably okay or are okay. It's only if you start getting really, really conservative or you start to have some concerns. And so in the original seismic study, we thought, well, we're going to have to reline at least one of these pipelines with something more flexible. Based on the results of the more detailed results, we're kind of thinking that, well, no, we really don't have to do that. It's okay not to reline any of the pipelines because even in an extremely low probability event, the best estimate is these pipelines are going to be okay. If there is something wrong, well, maybe it's most likely going to be a leak. So we backed off our original $75 million estimate for upgrading the Cedar River pipelines in Renton. And we've come down to maybe on the order of 5 to 10 million if we just do the flexible couplings at the interfaces, which I think are definitely needed, and maybe an additional 5 million if we decide to do something with Circle 2 at the Black River Channel crossing. Right now, we're just completing the options analysis. It was supposed to be done third quarter. We had some bureaucracy get in the way, but it looks like we're on track to have that done by the end of the year. So tentative schedule, as I mentioned, well, the options analysis is supposed to be done. We're a month or 2 behind. We would bid the contract 2025 third quarter with completion 2026. There really needs to be an asterisk with those numbers or with those dates, just because in our discussions with Renton, there's a potential washdot project where the utilidors come out from underneath the freeway, and they're talking about building a skyway or something like that. And so that's something that we're going to have to coordinate with. My understanding is a couple of those office buildings are going to be demolished. So like I said, I have to put an asterisk on those dates because we are going to have to coordinate this with Renton and WashDOT depending upon their project schedule. So any questions on the Renton project before I zip on to the next? Going once, going twice, okay. And then finally, we took a look at what it would take to put in a seismic resistant pipeline that could withstand fault ruptures along or through either the Seattle fault zone or the southward of the Iron fault zone. This picture over here on the right is from the 1999 Chichi earthquake in Taiwan. This is an 80-inch diameter, over 1 inch thick, welded steel pipeline. And you can see it was no match for the 2 or 3 meters of fault rupture they had. It just shows you that when you do get fault rupture, we have these massive displacements over a short period. The ground usually wins. So this shows the 2 fault zones that our transmission pipelines cross. Down here we have the Seattle fault zone. This north part is called Zone A. The south part in here is called Zone B. It extends from maybe a half mile to a mile north of the Fauntleroy Ferry Terminal up through downtown, middle of downtown Seattle, underneath the stadiums and all that. I'm sure you're aware of that and heard that. Southward of the Iron Fault, the active parts extend from about here to about here. Both zones are 4 or 5 miles wide, which creates some challenges just because it's not like, you don't have to design for just 200 feet. You got 4 or 5 miles where the potential rupture could occur. So that creates some challenges as far as budgeting and whether it's worthwhile or not. Again, another challenge is the Seattle fault zone. It may rupture over here and rupture right under the Eastside supply line and leave the Cedar River pipelines intact, or it may rupture here, affect the Cedar River pipelines, but the Eastside supply line will not experience the rupture, or it may rupture out here under Bainbridge Island and leave both the Cedar River and the Eastside supply lines fine. So there's a lot of uncertainty, and it's low probability, and so that's kind of like why we're thinking that, well, maybe we don't have to upgrade for fault rupture, or at least design in the future for fault rupture. Basically, some mechanics. This side here over on the left would be south. This would be north. As the spot is being compressed, there's a fault plane where this southern portion overrides the northern portion. What happens when the northern portion pushes back, you get some back thrusting. So that's why they call it on the southern portion Zone B, where you have the back thrusting. Zone A is where you get the main thrusting of the fault zone. These are the different models or assumptions they made to model fault rupture. They looked at a couple of different angles, displacements, the amount of displacement, or the width of displacement. For here, here you have 1 meter over 1 meter over 10 meters, 3 meters over 10 meters. Here you have a longer displacement and more gradual thrust here. These were the Seattle fault zone assumptions. Going down to the next slide is the southward of the Island fault zone rupture obstruction assumptions. In general, the displacements on the southward of the Island fault are not expected to be quite as large as the Seattle fault, but there's still a lot of uncertainty. And even if it's only a meter, if you have a concrete cylinder pipe, that concrete cylinder pipe's not going to do very good. In fact, even a welded steel pipeline might not do very good. Just a couple pretty pictures of the Ansys analysis. They're looking at joint rotation, both the tensile and compressive stresses, and just showing the different stresses for one of the cases. These are the demand. What's important here is the last column in this slide. And so for each of the 3 tables, the demand capacity ratio, DCR, anything under 1 is good. Anything over 1 is not good. As you can see, if you use welded steel pipe, even if it's butt welded, you can get some pretty large demand capacity ratios. I wouldn't get too freaked out by these 85s and 134.2. I mean, after a while, the pipe becomes plastic, and so they really don't mean anything. But like I said, if it's over 1, that's not good. If you look at the HDPE assumptions, you get demand capacity ratios, which are a little bit more reasonable, on the order of 2 or 3. And I can't see it on my computer, but because it's blocked out, and sorry, the slideshow is not working. But if you look at the demand capacity ratios for earthquake resistant ductile iron pipe, they are all less than 1. And for both the South Whidbey Island and the Seattle fault zone. The issue with not going ahead with using ERDIP everywhere is, number 1, the expense, and how much of an additional expense is somewhat debatable or even somewhat unknown right now. There was a recent project Metropolitan Water District, MWD. They were putting in 2 miles of earthquake resistant ductile iron pipe, 104 inch, 104. Very large pipeline, ductile iron pipe through 2 miles, a 2-mile fault zone. And their bid prices on the material, they have parallel lines. They have an ERDIP line in the same size 104 inch welded steel line. And the material cost for the ERDIP was 50% more than for the welded steel. I've had trouble finding what the installation costs are, or at least what the differences are. I would have to believe, my opinion is that the installation costs are going to be somewhat similar. And that is, it's not very easy to put in a 104 inch pipeline, regardless of what type of pipeline it is. I don't even think you can butt weld a 104 inch steel pipeline just from the fit up problems. But even if you're lap welding, I can see you having a lot of problems. And so, at least my opinion is, without having any numbers to back it up, is that the installation costs are probably somewhat similar, which would mean the overall costs are, maybe on the order of 10, 15% more for the ERDIP, but that's just me guessing. As it is right now, we decided that we're not going to be using ERDIP through the fault zones just because of the expense. So, like I said, that's where things are now. Before I move on to the Eastside Riverton project, are there any questions, comments, or? Okay, I will move on to Eastside and Riverton. Eastside Reservoir, 30 million gallon DYK tank, largest tank of its kind when it was built. Riverton Reservoir is kind of a weird one. Pre-stressed concrete panels. It's also post-tension. You can see some of the post-tensioning buttresses right here. Both tanks were estimated to be seismically vulnerable by the Seismic Study. So we've started taking a closer look at both of these reservoirs. Switching to Riverton first. It's over by the airport. If you're not familiar, you can see it if you take off to the north and look to the east down on the ground. It's sitting on undisturbed glacial till. Our initial findings from the seismic study was that this reservoir was going to be very vulnerable, and that's kind of what we've been able to back up during this follow-on study, even though not vulnerable and kind of the spots we expected it to be vulnerable. For both reservoirs, and this is a slide, it's not in the original presentation, but Kathy will get you this final presentation after today. We're using soil structure interaction. And the advantages of soil structure interaction is that it more accurately models what happens during the earthquake. Traditionally, when you have a structure, the foundation of the structure is assumed to essentially move rigidly with the ground when the ground moves. What happens in real life is that the ground pushes on the structure. As the structure is vibrating back and forth, it pushes back on the ground, which pushes back on the structure, et cetera, et cetera. And so you get a lot more damp-like performance or response to the structure. And this usually leads to lower structure forces, which can save you money in design. And so we are using SSI for both the Eastside and Riverton reservoirs. We're doing a check. In fact, if you use, the code says you can use SSI, it's becoming a lot more popular to use, but the current building code says if you do use SSI, there are limits into how much you can reduce the force over traditional analysis. So you want to do a traditional analysis anyway to make sure your SSI modeling seems reasonable, but you're also forced to use it anyway, just so you can make sure you're still in compliance with the code. This is a finite element LS Dyna result from Riverton Reservoir showing the hoop forces. They get up to around 600 kips per feet. And that does cause some problems, which I'll show you when I show the summary table, the demand capacity ratios. This is the roof and wall displacements, and hopefully, okay, it's playing full speed. That's good. And so there are two natural periods for a reservoir. One is the sloshing period, and the other is the impulsive period. That is the rigid structure. the water kind of moves a little bit independently of the structure. And for both Riverton and Eastside, the sloshing periods are in the order of 18 seconds. So as you see this move back and forth, this is a 15-second loop with some of the strongest ground motions. You really don't see any effects of the sloshing, but what you do see is impulsive, the more rigid motion, and the natural period of the impulsive motion is around 0.3 seconds. So it's quite a bit of difference, 0.3 versus 18. Going down to the next slide here, this just shows the displacements, the wall forces and tank displacements. You can see the tank and the columns move around inside a little bit with this video right here. And this table here sums up the demand capacity ratio, DCR, for different assumptions. The UHS 72 would be a 72-year event, 10% probability of exceedance, 475, 50% probability of exceedance in 50 years. The UHS 475 would be a 10% probability of exceedance in 50 years. 975 is 5%, and then the 2475 is 2%. And this shows the different demand capacity ratios for different failure modes. Obviously, what jumps out is the roof to wall connection. And this is low enough that we probably experienced some damage in the Nisqually earthquake. And I'll show you why we didn't see it. You can see the wall to foundation connection is another area of concern. Going to the next slide, just zeroing in, this is the roof to wall connection. It's all kind of hidden and buried. And so there's probably some bending and distress around the steel pipe in the Nisqually earthquake. We didn't see it. Obviously, because it's all covered up with concrete. You can see there's not much of a connection, the wall to footing connection. So you can see why that there would be some problems down here. These roof to walls connections always kind of, well, they're puzzling to me because it's damaged, but is it something that you really need to spend a lot of money to upgrade it with? Just because if you have damage to the roof wall connection, you may have some water quality issues, which you're going to have anyway after a major earthquake, but is going to affect the overall functionality of the reservoir. And that'll also come up when I talk about the Eastside Reservoir. When you talk about separation of the wall from the foundation, or any cracking on the floor or in the wall, that's something where you lose containment, and that's something that definitely needs to be dealt with. This is a new slide. I think in the original deck it just said TBD. Well, this is the TBD. These are the preliminary Eastside Reservoir results. Again, looking at the demand capacity ratios, you have a couple of different areas where you have demand capacity ratios over 1. Not surprising that the roof to wall connection, it's greatly over 1, and we saw that in the Nisqually earthquake. Even that small earthquake where there were issues right here, where basically you have a sawtooth roof and it separated from this side and kind of compressed against this side. Just like the Riverton Reservoir roof to wall connection, okay, it's not going to work, it's going to fail. This reservoir is buried. So there will obviously be some water quality issues, but we're going to probably have a boil water order anyway. And so it's something that you really need to address unless it's going to affect reservoir functionality. What's more concerning is down here, if you look at foundation sliding, and this would be the foundation part that the wall's left on. If this starts to slide, it's going to crack with the rest of the foundation. If you have cracks in the foundation of the tank, obviously the tank's going to drain out. And this is definitely a functionality concern. Again, with some of the DCRs that are over 1 on the wall, if you have cracks in the wall, water drains out of the wall, that's also a functionality concern. And so those are 2 issues that we're going to be looking at addressing.
Bill, can I interrupt for just a minute?
Yeah.
I think this is interesting for those of us who are technically focused. Couple things going on here. For those of you who have already done seismic upgrades for reservoirs, you look at the roof to wall connection. There's a number of ways to strengthen that so that roof shear carries to the wall. And for those of you who've probably poured internal concrete rings in order to help with the foundation sliding, as well as the wall to foundation connection, relatively tried and true things here. And when I look at these demand to capacity ratios, what you're looking at is where is it over 1? That means the shaking is too much for the capacity of that particular structural element. And then you also look at, is the demand capacity ratio over 1 for the lowest earthquake or the highest earthquake or somewhere in between? And so one of the arts of options analysis for seismic upgrades is, what is the standard you're going to design to? Do you want to make sure that the whole thing performs flawlessly after a 2,500-year earthquake? Do you want to make sure that it still performs, but there's some damage that you can fix later for less cost? Or do you want to take some risks for a much lower cost? And so for me, the interesting thing about options analysis that we'll be doing is looking at that risk and cost trade-off, because we're trying to keep rates affordable. We're also trying to make sure the system performs adequately overall, so that if some parts are not operable, others take their place. So anyway, I think it's an interesting discussion that we'll work through as part of the options analysis. And Bill, did that generally make sense, or am I overstepping my bounds here?
No, I agree. And if you look at these numbers for the 475 event, 1.02, 1.05, it's, if you're willing to accept, more risk for a, higher level earthquake, then, it becomes debatable whether you really want to do something. And then you also have to keep in mind the tank expected life. And so, we'll probably be replacing this tank in 100 years. And so it's not like it's going to be around for 2,400 years to get up.
Another interesting thing is, in addition to the conventional, let's, make some flexible but permanent connections from the roof to the wall, let's pour an internal concrete ring, there's other ways to attack this. So if you have potentially a situation where you might have wall cracking during a major earthquake, but it's not structural and that the reservoir won't collapse, the issue is water quality. You don't want the water to leak out if there's cracking. And so we worked with the consultant who made some pretty major design errors on some of our reservoirs 10 years ago. They paid for the retrofits, but in what they did some of these elements I'm talking about, but in another part of one of our reservoirs, they paid to have the a coating put on the walls where cracking might be anticipated, so that the wall wasn't going to fall down, but it was going to leak. And the coating then made the possibility of leakage much less after a major earthquake. So there's a lot of interesting ways to attack this kind of an issue. Just like a previous question was about pipeline upgrades, do you go replace all the pipelines? You can, but it costs the most by far. Do you wait till the pipelines are ready to fail or ready to be replaced and then replace them with more seismic resistant? That buys you 30 years of defrayed costs. What do you do in the short term? Do you stock spare parts, make sure you have the ability to replace things, maybe spend some money on some targeted replacements at May Creek and Coal Creek, for example? So I think the options analysis is just fascinating for seismic in a way that's much more complicated than, I got a development, it needs more storage, I got to build a tank. So it's much more nuanced, and we're happy to talk you more through these options once we get further down the line.
When you're looking at 800 million to make everything, seismic resistant, even if you had that money, you can spend it in the next year. You could not spend it in the next year just because there's no way you could do that many projects. And so I think it makes a little bit more sense to realize that you're not going to make everything better overnight, but to be prepared that if you happen to get unlucky and something, the big earthquake comes before you can make everything better, that you're at least prepared for it and can mitigate the effects. So, and it's from a funding standpoint, it's kind of challenging because you're spending the money now, but you're not getting the benefit until later. And from a political standpoint, well, my term is up in 4 years, so I'll live with the risk. But from a long-term standpoint, I think it's the best thing to do. But you have to be able to, make that case. The one thing that I think you absolutely have to do, though, is you have to build new stuff right. If we were talking about a new reservoir, I would say all these values, these demand capacity ratios here at 2475 should be below 1. So, and that's, to me, that's pretty straightforward and really not subject to much debate. Some of these other things are a little bit more debatable.
Yeah, I think Bill's absolutely right about that. And so just as a reminder, we're telling you about the things that we've learned in the transmission system, the pipes, as well as 2 of the reservoirs that were early identifiers for improvements. But then the big picture, stockpiling the spare parts, having the emergency response plan that's earthquake specific, having this overall strategy for quick response as needed, seismic design standards for new pipes and reservoirs so that you build it right the first time when you're building something new. That's what you're seeing today is part of a much bigger picture.
One thing I'll mention, to me, one of the big things is earthquake resistant ductile iron pipe. And this is mainly at the distribution system level. And so, this is supposed to be a transmission meeting, but it's great. The stuff is proven, it works. There's no doubt about it. However, it is something new, and at least at SPU, we have had our challenges with it. And so this gets under the category of when you build something new, build it right. And so when I say when you build something new, do it right, it sounds like something simple to do, but it's not always something simple to do. And as an example, on the distribution level side, we have a lot of projects we're chasing around the Seattle Department of Transportation, and they're federally funded projects, which basically means that you have to follow the Buy American rules. And getting an earthquake resistant pipe that with all the fittings that is in compliant with the Buy American rules is challenging, and it causes a lot of pain to some of our staff. And so I don't know what they say behind me about my back, but I guess I probably don't want to hear it. So it sounds easy. When you build it new, do it right, but it's a lot more difficult than that. Final slide. This is just from March of this year. These are the projections for over the next 10 years or so for our transmission pipeline projects. No real change, big change anyway. If there is a change, it's in right here for the Eastside Reservoir, for the circles in Renton, where we had the options analysis being done by 3rd quarter. It's going to slip into 4th quarter this year. As I mentioned, the construction schedule here might be subject to change just because we're going to have to coordinate with WashDOT and Renton. But so far, everything looks like it's on track as shown in the schedule. So, and with that, are there any general questions or?
Nice compliment from Andy and Bill. Nice job presenting. That's in the chat.
Andy just wants a free meal.
You
You
know
guys
where.
We have a hand up, I see, from Jay.
Yeah, thanks. Awesome presentation. You've overwhelmed me. Obviously this would be something that the Cascade membership would love to have a copy of this and digest and sort through. My question is going to be kind of simple though, or basic. The membership relies heavily on what I believe is the Cedar Eastside supply line and the Told Eastside supply line. And I'm wondering what you guys are doing with logistics for materials, anything that would bring those lines back in service in the event of an event, and whether particularly if one or both bridges go out, and if you've considered storing commodities on this side to have it closer to be brought into play.
Yeah, we have a project to purchase spare materials, and it's been stop and start. And right now we're kind of in a stop zone where, we've gotten as far as we know what we need, and we've identified tentative sites for where those materials and other equipment should go. But that's as far as we've got. I mean, we have tentative sites, but we haven't finalized sites.
And
It's a very important, I mean, your question is outstanding because it is going to take a while before we can get our transmission, all of our transmission pipelines to be seismically resilient. In the meantime, we need to be prepared in case something does happen between now and then.
just as a follow-up here, Bill, can you tell Jay and the group a little bit more about the kinds of materials, the pipes, butt straps, just to fill in a bit of the details of what we're looking to order?
Well, we're looking at everything. Well, we're looking at everything from, 8-inch lines in our distribution system up to, there's a couple 80-inch lines up on the toll. And so we're looking at, reducers, so we don't have to have the exact, pipe size for every pipe, but, we can use, and also obviously butt straps is another main component on the distribution side. I can't think of the things you put around. The things you put around the pipeline to fix a distribution pipeline break, and I'm having a mental.
Bell joint clamps?
Repair clamps. Yeah.
Hey,
Simple word.
Bill, this is Kathy. Can you pull your presentation down so that we can see each other better while we're discussing questions?
Okay. Yeah. That worked.
Yeah, and I think Steve from Redmond had the next question.
Yeah, great presentation. One thing you threw out at the very beginning was an $800 million price tag over 75 or 100 years. And I wondered, just $800 million in 2020 dollars or $2,300? What's that $800 million?
It's
Talking about.
actually it's $2018, which, as we're finding out, is a lot different than $2022.
Yeah.
Unfortunately.
And then general strategy for that big dollar.
Well, it's not, like I said, it's not all in 1 year or even 10 years or 20 years. It's part of the SBU strategic business plan. And so the money has, has been budgeted for.
Yeah, the idea is that generally speaking, we bond against major capital projects. And what we're trying to do is put the seismic projects in with the other stuff, aging infrastructure, dam safety, you name it, climate change, resiliency, that sort of thing. And so the idea is to segment these out so that we can go and fund these CIP projects within the context of our overall CIP, and then spread it out to reduce some of the rate impacts. We tend to bond about 70% of the cost of the CIP project, pay the rest with operating cash. We're also looking for the brick grants, the building resilient infrastructure something. I can never remember the C from FEMA. They started ramping up the funding considerably in the last year or so, and we're trying to figure out what those key criteria for getting funding is. So these seismic projects feel like good fits for that. We're also working with Tacoma and Everett to try to do something regionally in terms of lobbying at the state or federal level for, this was actually before they started getting the infrastructure bill in. Years ago, we were thinking, should we do some kind of regional thing that feels like a Yakima Basin storage kind of line item-y kind of lobbying effort? So we've been thinking about doing that as well to offset the rate impacts.
Cool. Thank you.
Next question, Doug from Bellevue.
Hi, thanks a lot for the presentation. It's a good update. I just wanted to add that, so we did a seismic assessment for Bellevue, and one of the things that we found was that you talked about if something's nearing the end of its useful life, you're going to replace it, and at that time it becomes more resilient. Our consultants, we had them develop a little table regarding code, because sometimes code is actually doesn't meet the expectations because it's based on assumption of how critical the structure or the building is. And sometimes it doesn't take into account the broader economic impacts. It just says, well, is this going to fall on a person, right? So that's just something to look out for. Sometimes you actually want your criteria to be more stringent than code requires.
Well, the newer codes are becoming more performance based.
Mhm.
And so it's, in the old days, you basically took the ground motions and you multiplied those ground motions by 2/3 and said, okay, if you design it for 2/3 of the ground motion, then you'll have enough flexibility in the structure that, it'll be damaged, but people will be able to walk out alive. You may have to bulldoze it after the earthquake. The approach now is, they're using important factors and things like that, and you can design for functionality. And so we're basically using risk category 4. Very simplistically, we're using risk category 4 with an important factor of 1.5, and with the idea that it'll remain functional for the 2475 earthquake. And when you come
Exactly.
with reservoirs, it becomes a little bit more complicated, because cracking can be acceptable in a concrete building, but cracking in a concrete reservoir obviously is a different matter if the water drains out through the cracks.
Yeah, I think our take home was just make sure that you talk with the structural engineer so that they understand, because they might have a different assumption.
You have a great point. You got to make sure that the structural engineer understands that this needs to be functional, not just life safety performance objective.
Yeah.
Because those are two completely different. And like I said, cracks in a concrete building in a 2475 earthquake, everybody walks out, you'd be extremely happy. Cracks in a concrete tank like Eastside Reservoir, not so.
Yeah. And then I was going to ask if the Infraterra study, if that can be shared, or is that too sensitive?
It can be shared.
Okay.
And I'll make sure Kathy has, get you a copy.
All right. And then is there any updates to SPU's public messaging? I know you have a website for the 2018 study. So when we get questions, I send people to that, right?
Yeah, honestly, the general message is high level enough for the public on the website that we're not seeing that much need to update the website. It basically says, look, we're trying to be seismically resilient, and here's a link to the seismic study. If anything, we may put a link to the transmission supplemental study up as well. We haven't got to that yet.
Okay, great. Thank you.
I would say that there's kind of a twofold message we're trying to help communicate with you on. And the first one, obviously, as customers who get Seattle water for your own customers here, we want you to feel bought into the seismic planning and the fact that a portion of your rates that go to Cascade and then Cascade to us funds the capital and some of the operational needs for the regional system. So that's the biggest thing today. And questions are really, that's a good area to focus on. The second thing is you all have your own retail distribution system that you manage, just like we do for the city of Seattle here. And some of the elements that we did for the seismic study are specific to Seattle. So for example, Bill talked about the seismic standards, design standards for new facilities. And one of the biggest things is when you put in a new piece of distribution pipe, when is it seismically standard and how seismically standard should it be? So those standards are really key to have as part of your own retail service area. If you were to do something like Bellevue did as well and look at your own seismic study that looks at what's the performance of your own retail system, part of the things that you just heard Bill and Doug talk about are really key. Like, what do you want to make sure doesn't fall down and hurt someone? What do you want to make sure doesn't fall down but also stays in performance and still makes the water system go for you? So these are the kinds of things I think I would encourage you to all think about as you manage your own system, and as well as things like stocking spare parts. While it may not be 72-inch pipe, how much 8s and 12s do you have, bell joint clamps, other repair materials, these sorts of things. In the event of an earthquake, you probably need to get them fast, and no one's going to make them all that fast.
the water mains is a really important point, and it dovetails on some of what Doug said, because there really are no standards or requirements for water mains. And as far as I know, you can put in lead joint cast iron if you can find it somewhere.
If you can
That's
set up for a lead joint, you can put it in.
so, and my opinion is wherever you have the potential for permanent ground displacements, you should be putting in earthquake resistant pipe. And it, depending upon the level of ground displacements, it doesn't necessarily have to be the full meal deal Kubota, but it should be designed to resist what ground displacements are reasonably expected at that site. But there are no requirements to do that. And like I said, from our own study, SPU internally, we're looking at 1,400 breaks in a magnitude 9 Cascadia event, 2,000 magnitude 7 Seattle fault event. Even if every other piece of infrastructure performs perfectly well, that's going to shut us down for a long time, just getting all those repairs made. And so it's something that, as your asset management programs, as you're replacing pipe for condition and other reasons that you need to keep in mind and make sure you get in earthquake resistant pipe where you need it. My own Nostradamus prediction is that we're going to follow the same route that the Japanese took. And that is, they started out just putting in earthquake resistant ductile iron pipe only where they needed it. They had numerous earthquakes, earthquake resistant pipe, 0 failures. They had breaks in their other pipelines, and they said, we're going to stop messing around with this. And now most utilities are putting in, Japanese utilities are putting in earthquake resistant ductile iron pipe everywhere. I think we still have a little ways to go as far as getting us up to speed on being able to handle the construction and design issues with earthquake resistant pipe, but I think that's where eventually we're going to head.
Yeah, and when it comes to the earthquake resistant ductile pipe, I mean, if we have other questions about some of what we talked about today, feel free to interrupt, because Bill and I will talk for a little while if you like, otherwise. But some of the things that we're learning here is, first of all, if you can't use the Kubota pipe on a project because it's got Buy American, you got sort of limited options on what to do if you want to stick with ductile iron pipe. So you have 2 American competitors, and the Kubota system is pretty elegant because you have sticks of pipe. It's just the joint, the bell and spigot, is specially engineered for pull-out resistance and bending and that sort of thing. The 2 American competitors that we've used both, people are still learning how to use these things. And one of them is a little bit like Kubota in that it's got individual sticks of pipe with a special bell and spigot joint, but the sticks of pipe are half length. So instead of 20s, you got 10s, and you got twice the number of joints that can be fussy and go wrong. And that's not a great system, but it works. And then the other competitor here, they have a different design altogether. They have regular old ductile pipe with the bell and spigot, but then there's this big red dealie that the bell and the spigot go into. And then so instead of just bell, spigot, bell, spigot, bell, spigot, you got bell, spigot, dealie, bell, spigot, dealie, bell, spigot. So it's just complicated, And I don't know that we're really sold on either of the competitors. I mean, Bill, are you feeling pretty good about them now?
First, I'll make a point is earthquake resistant pipe doesn't have to need to be ductile iron pipe.
Right.
It can be HDPE, or there's PVCO, which is basically molecularly oriented polyvinyl chloride pipe, and those also do very well under seismic loadings. When you get into just a ductile iron pipe, the issue is Kubota's been putting their stuff in for 40 years. It's proven track record. They know what they're doing, blah, blah, blah. And there's no doubt it's going to perform as advertised. The American pipe product is, they thought everything out. They tested it. And based on their tests and their design, there's no reason to expect that that's not going to perform as advertised. The US pipe product is basically, they took their existing TR Extreme product and they said, okay, this is our earthquake resistant ductile iron pipe product. As far as the joint rotation and expansion and contraction, it's a little more than half of the ISO 16134 standard for earthquake resistant ductile iron pipe. which as Alex mentioned means, okay, well, if you're going to use it to meet the standard, you have to put in 10-foot segments instead of 20-foot segments. The other issue is one of the big advantages or big selling points or why it works of earthquake resistant ductile iron pipe is a joint pullout strength. And so that's the joint pullout strength needs to be 17,100 pounds times the diameter in inches. So for like an 8-inch pipe, you look at 200,000 pounds, which is way, way beyond what's normally out there as far as typical pipe or restrained joint pipe that you put in for just thrust loads. The US pipe product, their TR Extreme joint does resist those. They've tested it and it does resist those loads. It's a little less clear about some of their fittings, whether they'll resist those thrust loads. And so that is, if you have a fitting in there, the pipe pulls, well, the pipe stays together, but just pulls out at the fitting. Now, they're probably very close to being able to resist those loads or maybe even exceeding those, but I haven't seen independent third-party testing that shows or proves that they can meet those thrust loads for their fittings. And so that's kind of why I get, I'm a little bit hesitant with the US pipe product. Now, somebody from US pipe is probably going to call me up now and yell at me, but I'm used to it. Kubota and American people have also called me up and yelled at me. So that's.
And like Bill said, we have tried HDPE in a few cases. We standardize on ductile for distribution pipe, and we like steel. I like steel the best for transmission. We've had limited, well, some success and some not so success with concrete. And HDPE seems like it works okay. Our crews are not that comfortable tapping it. So if you have a distribution pipe and your crews are not set on how to tap it and fix it, I would encourage you not to use it, plain and simple. So we've used it in cases where there's very limited service connections, or it's just plain old transmission pipe and there aren't service connections. You also have to be worried about permeability against gas and other BTEX kind of products that get through the plastic. And then there's this whole philosophical debate about plastic versus metal, using a gas-based product, or an oil-based product versus a metallic. So there's a lot going on. But for example, on the Tolt pipeline area where there's some sliding, we're just about done with taking an old section of concrete pipe, Tolt Pipeline 1, and we are pulling a section of HDPE through it so that it will resist movement of that slide area better over time, even though the cost is you have a reduced diameter because you're pulling pipe through. And gosh, back in the 80s, for some of the concrete pipe on the Tolt that failed twice, we slip lined some of that concrete pipe with ductile pipe back then. So these are all good tools in your toolbox, whether it's large transmission or your own retail service area.
Yeah, the bottom line is I would suggest that utilities continue talking with each other and discussing their problems and their solutions to these problems, because earthquake resistant pipe is something new in this country. And, the utilities I've talked to down in Portland and California are all struggling through the same issues that SPU is. So.
Oh, I saw, Henry's got your hand up.
Yeah, thanks, Bill, for that presentation. I thought it was very comprehensive and very informative. I want to check my understanding on the CIP budget / budget process with respect to seismic upgrade of transmission pipeline. I heard earlier you mentioned about transmission seismic upgrade. There's a maybe budget program, sub-program, and it's segmented. So my question is there a chance for doing your budget process that gets ranked against other CIP projects in your non-seismic upgrade program and get pushed out because other projects takes priority, or you earmark out a budget to accomplish the seismic upgrade program?
Seismic is a big part of the overall CIP priorities. And I think all of us would say when we're doing our CIP budgeting, there's a constant push and pull against affordability and which projects should be funded. And how do you balance a pump station upgrade versus a need for some new pipe versus a building upgrade for one of your offices? I guess I would say that the reason that we do long-term planning, so any of you, if you want to go online and look up our 2019 water system plan, one of the last chapters is the capital and operating strategy. So we have a graph in there that shows the next 20 years of capital upgrades, our best guess. We're reading crystal balls to the best of our ability, but seismic was one of the key tenets going into that overall blend. And the reason we do 20 years of forecasting is in part for our decision makers, for Andrew and myself, for our electeds, the council, mayor, to get some early visibility on all the things we need to do and what we think it will cost. So that gets us ahead of any discussions about, well, you need to cut the budget, what will go first, and that sort of thing. If we do get into that point, some of these key elements like seismic, they should be the last things to go if there is a cut exercise. And thankfully, we're able to, with these forecasting tools, we're able to get ahead of these sort of budget request cut exercises because we're trying to look forward all the time.
So what I got out of this is it's not impossible, but very unlikely it gets bumped or get cut.
Yeah, I mean,
deprioritize.
Really, this likelihood of any projects getting bumped is the same likelihood as for any of us who manage utilities having budget issue that you have to look at. You know, what are your priorities? What can come off? Or what do you have to find alternative funding for? So it's very unlikely, but it's not zero.
Okay, thanks.
Linda, you have a
Yes,
question?
thank you. Thanks, Alex, and thanks, Bill, for the presentation. Really informative. Kind of a follow-up question to Henry's question. And I was just thinking about the information that you said about planning to upgrade the backbone pipelines in the same time frame that they would need to be replaced. So you're gonna upgrade them when their useful life is coming up, and barring that they break before that, and you're gonna upgrade them to the new seismic standards. So that made sense. But I was just wondering, you were saying in the 2019 water system plan, if I heard right, you have a projection of when those projects would be scheduled out for the next 10 to 20 years, right? So if we wanted to see a certain segment of the supply lines on the east side, when approximately would they be done, to see how they match up with our own CIPs, and just to know, what the regional system upgrades are going to be like in the future? That would be the best place to look, is in the water system plan, or is there some other auxiliary plan that goes with that?
Linda, I think the best place to start would be, and this is also available on the web, or we can send it around. It's just the 2018 seismic study. So in both the executive summary and one of the end chapters, there's that 50-year, 75-year plan for CIP. However, we did focus on discrete elements here. For example, the Cedar River pipelines at Renton and West Seattle pipeline. We described 5-year increments in which we anticipated those capital projects would go. And to tell you the truth, I can't remember what we did with the Cedar Eastside supply line. Bill, do you remember if that's lined out specifically, or if it's part of, we had a set aside for transmission work as needed in any given year?
We don't have a set aside for any seismic upgrade projects, other than potentially the Serpent crossing of the Cedar River, or the Cecil crossing of the Cedar River.
That's right. And we did put that in. We could find the schedule and bring it up if we had time. And that's right, we were looking at that 1 point area of the crossing of the river.
That's potentially a very critical area.
Yeah, that would be helpful to know. Maybe that could be provided to whoever might want a copy.
Yeah, we can send that out.
Thank you.
Henry, do you have another question? You're muted.
Sorry, I should lower my hand.
Yeah.
Sorry about that.
One thing too is it's a lot of information and a lot of detail here. Obviously, we've been thinking about this and trying to do something about it for a long time. This is your second time I think we've really talked to you about some of these details. So if you want to ask more questions, I think you could always forward those questions on maybe through Melina to Kathy. And we're happy to have follow-up discussions on this or other topics of the regional nature for the regional water system. In the meantime, I see some more hands up. Jay, did you have another question?
Yeah, I just had another kind of basic question, and hopefully it's not overly broad, but I know, the presentation had a high degree of engineering orientation today to understanding condition, potential failures. Is there any element of the analysis that takes into consideration where customer impacts would be, the number of customers that we would be impacted by failures, disruptions, and kind of takes into consideration the magnitude of the population impacted by certain types of failures?
Yeah, do you want to take that one, Bill?
Well, I think when we're doing our options analysis, that's one of the things, there's the probability of failure and the consequences of failure, and the number of customers impacted obviously falls under the consequences of failure. And so, yes, it does get considered. In case you're wondering, the FEMA recognized number is $105 per person per day loss of water.
Yeah, and I'm more interested in where are these customers, and if you guys are considering our customer demographics, or if you're just blanketly looking at the retail, or excuse me, the wholesale customers, as opposed to the individual Seattle customer base.
They all count the same, $105.
So you're using our customer counts in consideration of that.
In Seattle, has the program to, provide equity across its service area. And so that does get considered as part of the options analysis. So.
Thank you.
Linda, do you have your hand up for another question? Oh, okay.
Couldn't get to the unmute button. I just didn't take it down yet. Sorry.
Okay, you bet. Oh yeah, Kathy's posting a link in the chat here to the 2018 water system study. That's the seismic study. And you're welcome to go download that. You'll notice that 2 chapters are missing. They are the 2 chapters in which we went through and ranked by criticality all of our facilities in order to help figure out which should be upgraded first and which should be upgraded last or not upgraded at all. So those 2 chapters have been redacted, and we can talk you through those results if you like. The chapters themselves, we've tried to keep out of the public domain for obvious security reasons. But in terms of like Linda's question, the 50-year schedule where we tried to line out individual projects along the transmission system, which has now been to some degree updated by some of the graphics Bill showed you, that's available in both the executive summary and I think the last chapter.
Thank you.
We had quite a discussion with Sandy Doughton at the Seattle Times about how much of the study should be available and how much should be not available. that's where we landed. Other questions or thoughts?
And let's see, Doug. Looks like Doug has another question.
Yeah, related to that, I just wanted to say thank you very much for taking that on and talking with the Seattle Times and getting that information out in the public, because it has really greased the wheels of the skids for us in our study, because we're telling our commissioners and such, you know, this is going to happen, you know, and it's like they've already kind of been primed to hear it. So I'm just saying thank you.
Thanks, Doug. I'm glad somebody appreciated it, because Alex and I found it very challenging.
A very stressful time in our careers. All right, other questions or thoughts? We're happy to stay on the line if anyone has questions. If you have follow-ups or things occur to you after you sign off, Kathy Curry is our point of contact for any questions, comments, thoughts.
And I will send out Bill Hubach's presentation. I shared an earlier version through Melina that you may have seen, but he's since added a couple of additional slides. So the revised presentation I will send out will include those.
Yeah, Kathy,
Kathy, I'll send you a link to the transmission pipeline study, so you can.
And Kathy, why don't you send everything to me?
Yes.
I will. So I'll send that information out to everyone along with the link to this recording.
Great.
That'll probably take a couple of days, but we'll get that all to you all.
Perfect. Thank you.
And as Alex said, if any member staff have additional questions, you can send it to me. I can funnel them through Kathy, and Kathy can get it to the right people in SPU. I don't want to inundate you with emails, Kathy, so I could take that on and forward that to you. But, you know, just a huge thank you to Bill and Alex and the entire SPU gang for sharing this great presentation with us. It's been highly anticipated. We really appreciate the time and effort and all the great information, and look forward to continuing to partner. I heard you say before, Alex, that as you all move through the options analysis, there might be an opportunity to share how that's going further with us. So we'll probably keep in touch through our quarterly meetings with you.
Great.
Okay. So if there's nothing else, thanks to everyone from the member agencies for joining us. Again, Bill, Alex, Kathy, Andrew, everyone else. Thank you.
Thanks for the questions.
Thanks for the great discussion. Good to see you all.
Okay. Bye, everyone.
Bye.